July 28, 1976. Barents Sea, Soviet territorial waters. Major Brian Scholl pushed the throttles forward on his SR-71 Blackbird, feeling the twin Pratt and Whitney J58 engines respond with 68,000 pounds of combined thrust. The Mach meter climbed past 3.0, then 3.1, settling at 3.2. Altitude, 85,000 feet. Outside air temperature, negative 56 degrees Fahrenheit. Skin temperature on the aircraft's leading edges, 900 degrees Fahrenheit. Soviet ground radar had detected the SR-71 200 miles out. Air defense controllers scrambled 4 MiG-25 Foxbat interceptors from Murmansk. The Soviet pilots pushed their aircraft to maximum performance, climbing desperately toward 80,000 feet. Their engines, designed for brief bursts of extreme speed, screamed at full military power. At 78,000 feet, fuel gauges showed critical levels. The MiG-25s had reached their practical ceiling. Above them, the SR-71 continued at 85,000 feet, pulling away at 200 miles per hour faster than the Soviet interceptors could possibly fly. Surface-to-air missile batteries along the Kola Peninsula locked their radars on the American reconnaissance aircraft. Launch authorization came from Moscow. 6 SA-5 Gammon missiles, each weighing 10,000 pounds and capable of Mach 3.5 speed, roared from their launchers. Fire control radars tracked the missiles' climb toward the SR-71's flight path. At 65,000 feet, the missiles' rocket motors burned out. Momentum carried them higher, but speed bled away rapidly in the thin air. At 78,000 feet, the closest missile passed 3,000 feet below the SR-71, its proximity fuse failing to detonate because the enormous heat signature from the Blackbird's skin, 900 degrees across most of the airframe, overwhelmed the missile's infrared seeker. By the time Soviet controllers realized the intercept had failed, Major Scholl's SR-71 was over Norwegian airspace, descending toward its base in England. Mission accomplished. Another Soviet attempt to shoot down the Blackbird had failed. This pattern would repeat thousands of times over 32 years. Soviet forces would fire approximately 4,000 surface-to-air missiles at SR-71s during the aircraft's operational lifetime from 1966 to 1998. Not one would achieve a kill. For the Soviet Union, the SR-71 represented an impossible combination of speed, altitude, and invulnerability. Soviet air defense doctrine in 1966, when the Blackbird became operational, was built around the most sophisticated integrated defense network in the world. The Warsaw Pact deployed overlapping radar coverage from the Baltic to the Black Sea, with thousands of surface-to-air missile batteries and interceptor bases positioned to engage any aircraft attempting to penetrate Soviet airspace. The SA-2 guideline missile system, introduced in 1957, had proven its effectiveness on May 1, 1960, when a SA-2 shot down Francis Gary Powers' U-2 reconnaissance aircraft over Sverdlovsk at 70,000 feet. The SA-2's 60,000-foot ceiling had been sufficient to destroy America's previous high-altitude spy plane. Soviet engineers believed they had closed the high-altitude reconnaissance gap. American aircraft attempting to photograph Soviet territory would be detected, tracked, and destroyed. The SA-5 Gammon system, deployed in 1967, extended Soviet air defense capabilities even higher. With a theoretical ceiling exceeding 100,000 feet and missiles capable of Mach 3.5, the SA-5 was specifically designed to counter high-altitude, high-speed threats. Soviet military planners knew the Americans were developing advanced reconnaissance aircraft. The SA-5 would make such aircraft as vulnerable as the U-2 had proven. Soviet interceptor forces added another layer of defense. The MiG-25 Foxbat, which entered service in 1970, was designed explicitly to counter American high-speed, high-altitude bombers like the XB-70 Valkyrie. The MiG-25 could reach speeds of Mach 2.3 and climb to 80,000 feet. While these performance figures couldn't match rumors about the American SR-71's capabilities, Soviet commanders believed the MiG-25 provided at minimum a deterrent against sustained reconnaissance operations. American aircraft might penetrate Soviet airspace once or twice, But facing repeated MiG-25 intercepts, the reconnaissance missions would become too dangerous to continue. Soviet air defense doctrine assumed that nothing could fly above 80,000 feet at speeds exceeding Mach 3 without being vulnerable to interception. The physics seemed clear. At extreme altitudes, air density decreased to the point where aircraft control surfaces became less effective and engine performance degraded. At extreme speeds, aerodynamic heating would melt conventional airframes. The combination of extreme altitude and extreme speed represented engineering challenges that Soviet experts believed even American technology couldn't overcome for sustained operations. What Soviet intelligence didn't know was that American engineers at Lockheed's Advanced Development Projects facility, known as the Skunk Works, had spent 6 years solving exactly those problems. The result was an aircraft so far ahead of anything Soviet aerospace engineering could produce that it rendered the entire Warsaw Pact air defense network obsolete for high-altitude reconnaissance missions. The project that became the SR-71 began in late 1957 as Project Oxcart, a CIA program to develop a successor to the U-2. The agency needed an aircraft that could penetrate Soviet airspace at altitudes and speeds that would make interception impossible. Lockheed's legendary engineer Clarence Kelly Johnson proposed an aircraft built almost entirely of titanium, powered by ramjet engines, capable of sustained Mach 3+ cruise at altitudes above 80,000 feet. The technical challenges were enormous. Titanium, while offering the strength and heat resistance necessary for sustained Mach 3 flight, was extraordinarily difficult to work with. Conventional steel tools couldn't machine titanium effectively. Welding required inert gas environments to prevent contamination. Even drilling holes in titanium sheets required specialized techniques. The United States didn't produce enough titanium for the program's needs. Lockheed purchased titanium from the Soviet Union itself, using shell companies to disguise the purchases. Soviet metallurgists unknowingly provided the raw material for the reconnaissance aircraft that would violate their airspace for 3 decades. The aircraft's design reflected obsessive attention to every aspect of high-speed, high-altitude flight. The fuselage was long and slender to minimize aerodynamic drag. The delta wing configuration provided lift at extreme altitudes while maintaining stability at high speeds. The engine nacelles, positioned on the outer wings, were carefully shaped to manage airflow and reduce radar cross-section. Every surface was coated in special radar-absorbent materials that reduced, though didn't eliminate, the aircraft's visibility to Soviet radar. The Pratt Whitney J58 engines represented an engineering triumph equal to the airframe. Each engine produced 34,000 pounds of thrust with afterburner engaged. But the revolutionary feature was the engine's ability to transition from turbojet to ramjet operation at high speeds. At speeds below Mach 2, the J58 operated as a conventional afterburning turbojet. As speed increased beyond Mach 2.5, bypass tubes opened, routing incoming air around the engine core directly into the afterburner. At Mach 3.2 cruise, approximately 80% of the total thrust came from ramjet operation, with only 20% from the turbojet core. This transformation allowed the SR-71 to sustain speeds that would have destroyed conventional turbojet engines. The fuel system was equally revolutionary. JP-7, a special fuel developed specifically for the SR-71, had an extremely high flash point. It wouldn't ignite below 500 degrees Fahrenheit. This provided enormous safety benefits. If a Soviet missile detonated near the SR-71, shrapnel might puncture fuel tanks, but the JP-7 wouldn't explode or even ignite at normal temperatures. The downside was that JP-7 couldn't be ignited by conventional means. Starting the J58 engines required injection of triethylborane, known as TEB, a chemical so pyrophoric it ignited spontaneously on contact with air. Each SR-71 carried enough TEB for 16 engine starts, 2 for each of the 2 engines at takeoff, with reserves for air restarts if needed. The aircraft's fuel capacity was 80,280 pounds of JP-7, held in 6 tanks distributed throughout the fuselage. But here, the SR-71 revealed another engineering challenge that Kelly Johnson's team had to solve. At Mach 3.2 cruise, aerodynamic heating raised the aircraft's skin temperature to between 450 and 900 degrees Fahrenheit, depending on location. The titanium airframe expanded from this heat. The fuselage literally grew 8 inches longer at cruise speed. Fuel tanks couldn't be sealed tightly because the expansion would crack rigid seals. Instead, the tanks were designed to leak on the ground and seal only when the metal expanded at operating temperature. Every SR-71 sat on a drip pan at its parking spot, with JP-7 slowly seeping from panel joints until the aircraft reached cruise speed and temperature. The first A-12 aircraft, the CIA variant that preceded the Air Force's SR-71, flew on April 25, 1962. Test pilot Lou Schalk reported that the aircraft handled beautifully despite its unconventional design. Over the next 4 years, Lockheed built 15 A-12s for the CIA and began production of the SR-71 variant for the Air Force. The SR-71 featured a longer fuselage, revised sensor bays, and a second crew position for a reconnaissance systems officer who operated the cameras and sensors while the pilot concentrated on flying. The first SR-71 was delivered to the Air Force in January 1966. The cost was staggering, $34 million per aircraft in 1966 dollars, equivalent to over $300 million in 2025 currency. For comparison, an F-4 Phantom fighter cost approximately $2 million in 1966. The SR-71 cost 17 times as much, but what it provided was strategic reconnaissance capability that no other system could match. The SR-71 became operational with the 9th Strategic Reconnaissance Wing at Beale Air Force Base, California, in January 1966. The first operational reconnaissance mission didn't occur until March 21, 1968, when an SR-71 flew over North Vietnam photographing suspected surface-to-air missile sites and MiG fighter bases. North Vietnamese air defense forces detected the SR-71 on radar and launched 6 SA-2 missiles. All 6 missed by substantial margins. This pattern of detection, attempted intercept and failure would characterize every SR-71 mission over hostile territory for the next 30 years. Soviet and Soviet-equipped air defense forces could detect the SR-71 on radar. The aircraft was large and flew at high altitude. It wasn't invisible, but detection meant nothing without the ability to engage successfully. Time and again, surface-to-air missiles would launch, climb desperately toward the SR-71's altitude, and fall short as the Blackbirds simply outran the threat. During the October 1973 Yom Kippur War, SR-71s flying from Cyprus provided strategic reconnaissance of the entire Middle East battlefield. Syrian air defense forces, equipped with Soviet SA-3 and SA-6 missile systems, launched multiple intercepts. None came close. The Syrians reported to their Soviet advisors that the American reconnaissance aircraft was operating above 80,000 feet, at speeds their fire control radars indicated exceeded Mach 3. Soviet technical experts, reviewing the data, confirmed what they had feared. The Americans had deployed a reconnaissance aircraft that Soviet air defense doctrine couldn't counter. Soviet territory reconnaissance missions followed carefully planned routes that kept the SR-71 in international airspace, while its sensors photographed Soviet military installations from standoff ranges. A typical Baltic Sea mission would depart from RAF Mildenhall. In England, accelerate to Mach 3.2 over the North Sea, fly a precisely calculated course along the Baltic coast with cameras pointing sideways into Soviet territory, then return to England at high speed. The SR-71's cameras could photograph objects as small as individual vehicles from 80,000 feet altitude and 40 miles horizontal distance. Soviet bases 40 miles inland from the coast were completely vulnerable to surveillance, despite being well within Soviet-controlled airspace. Soviet forces attempted intercepts on every detected SR-71 flight near Soviet territory. The pattern was invariable. Ground radar would detect the SR-71 at ranges exceeding 200 miles. Air defense commanders would scramble MiG-25 interceptors from the nearest airbase. Soviet pilots would climb at maximum rate toward 80,000 feet, while ground controllers calculated an intercept course. But the intercept geometry was impossible. The MiG-25, with a maximum speed of Mach 2.83, couldn't close on an aircraft flying Mach 3.2. Even if the MiG-25 started ahead of the SR-71's flight path, forcing a head-on engagement, the closure rate gave the Soviet pilot perhaps 30 seconds to acquire the target, achieve radar lock, and fire missiles, all while flying at the extreme edge of his aircraft, his performance envelope, at an altitude where any aggressive maneuvering risked engine flameout or loss of control. Surface-to-air missile engagements faced even worse geometry problems. The SA-5 Gammon missile, Soviet's most capable high-altitude interceptor, had a theoretical ceiling of 100,000 plus feet and could reach Mach 3.5 speed. But those performance figures represented the missile's maximum capability in ideal conditions, launched straight up from sea level with no maneuvering required. Engaging an SR-71 required the missile to follow an intercept course that involved both climbing and accelerating while tracking a target moving at Mach 3.2. By the time the missile reached 85,000 feet, its speed had bled down to perhaps Mach 2.5, and the SR-71 was 50 miles beyond the engagement point. The September 1976 incident over the Baltic Sea represented the closest any Soviet missile came to an SR-71. Soviet air defense forces had positioned multiple SA-5 batteries specifically to cover the approaches that SR-71s used for Baltic reconnaissance missions. When radar detected an inbound SR-71, controllers launched a coordinated barrage, 12 missiles from 4 different batteries, timed to arrive at the predicted intercept point simultaneously. The massive salvo represented the heaviest anti-aircraft fire ever directed at a single reconnaissance mission. The SR-71 pilot, monitoring Soviet radar activity through his electronic countermeasures equipment, knew missiles were inbound but maintained course and speed. At 85,000 feet and Mach 3.2, he was confident in his aircraft's performance advantages. The missiles climbed toward intercept altitude. Fire control radars tracked both the missiles and the target, transmitting course corrections. At 78,000 feet, the leading missile passed approximately 3,000 feet below the SR-71. Its proximity fuse should have detonated at that range, but the fuse was overwhelmed by the Blackbird's enormous thermal signature. The aircraft's skin, heated to 900 degrees Fahrenheit by aerodynamic friction, created an infrared return so intense that the missile's seeker couldn't properly discriminate the target from background thermal noise. The remaining 11 missiles fell even further behind, their rocket motors having exhausted their fuel before reaching effective engagement altitude. Soviet radar operators watched in frustration as all 12 missiles fell back toward Earth without achieving intercepts. The SR-71 continued its mission, photographing Soviet naval facilities at Kaliningrad before departing the area at sustained Mach 3.2. Post-mission analysis by Soviet air defense experts led to grim conclusions. Arctic reconnaissance missions demonstrated another dimension of the SR-71's capabilities. Soviet ICBM fields in Siberia, strategic bomber bases in the far north, and submarine pens on the Kola Peninsula were all photographed repeatedly by SR-71's flying routes that Soviet forces couldn't effectively defend. The extreme cold of Arctic operations, outside air temperatures as low as -70 degrees Fahrenheit at 85,000 feet, created additional challenges for Soviet interceptor aircraft. MiG-25 engines struggled at extreme altitude in frigid air. Fuel systems froze. Hydraulics became sluggish. The SR-71, designed specifically for extreme temperature operations ranging from 900-degree airframe heating to -70-degree ambient air, operated flawlessly in conditions that grounded or severely hampered Soviet interceptors. The longest SR-71 sortie achieved during operational service was the final flight of the reconnaissance program. On March 6, 1990, Lieutenant Colonel Ed Yielding and Lieutenant Colonel Joseph Vida flew SR-71, tail number 972, from Los Angeles to Washington, D.C., via a northern route over Montana, arriving at Dulles International Airport in 64 minutes and 20 seconds, averaging 2,124 miles per hour. This flight, conducted as a publicity event to mark the SR-71's retirement from Air Force service, demonstrated capabilities that remained unmatched by any other aircraft 24 years after the Blackbird's operational debut. The speed records established by SR-71s during their operational lifetime remained unbroken by air-breathing aircraft. On September 1, 1974, Major James Sullivan and Major Noel Widderfield flew from New York to London in 1 hour, 54 minutes, and 56 seconds, averaging 1,435 miles per hour. The same route flown by commercial airliners takes approximately 7 hours. The SR-71 covered the distance in less than 2 hours, demonstrating that American aerospace engineering had achieved performance levels that commercial aviation wouldn't approach for decades, and military aviation still hasn't matched in 2025. But the SR-71's value wasn't measured in speed records. Its strategic reconnaissance contributions during the Cold War provided intelligence that no satellite system could match. While reconnaissance satellites offered broad area coverage and revisited targets on predictable orbits, the SR-71 could be launched on demand to photograph specific targets at specific times. During international crises, SR-71s provided real-time intelligence that helped American decision-makers understand rapidly evolving situations. The aircraft photographed North Vietnam throughout the war, providing targeting intelligence for airstrikes and damage assessment after attacks. Middle East reconnaissance during multiple Arab-Israeli conflicts gave American intelligence comprehensive understanding of military dispositions on all sides. Libyan military facilities were photographed after terrorist incidents linked to Libya. North Korean military developments were monitored continuously. Soviet naval activities in the Atlantic, Pacific, and Mediterranean were tracked and documented. In every theater where American national security interests required detailed reconnaissance, SR-71s provided intelligence that no other system could collect. Soviet attempts to counter the SR-71 continued throughout the 1970s and 1980s. The MiG-31 Foxhound, introduced in 1981 as an improved interceptor specifically designed to counter cruise missiles and high-speed reconnaissance aircraft, featured more powerful engines and improved radar. Soviet air defense forces developed new surface-to-air missile systems throughout the 1970s and 1980s, each generation promising improved high-altitude, high-speed engagement capabilities. The SA-10 Grumble, introduced in 1980, featured phased array radar and advanced seekers. The SA-12 Gladiator and Giant, deployed in the mid-1980s, were designed for ballistic missile defense and could theoretically engage targets at extreme altitudes. But by the time these systems became operational, SR-71s were conducting reconnaissance missions from peripheral routes that kept the aircraft in international airspace, beyond the engagement range of Soviet air defense missiles. The fundamental problem Soviet air defense forces faced was that the SR-71's performance margins were simply too large to overcome. A Soviet missile might be capable of Mach 3.5, but it had to climb from ground level to 85,000 feet, while also accelerating and maneuvering to intercept. The SR-71 was already at altitude and speed, requiring no maneuvering beyond minor course adjustments. The physics favored the reconnaissance aircraft overwhelmingly. The electronic warfare dimension added another layer of invulnerability. SR-71s carried sophisticated electronic countermeasures equipment that could detect Soviet radar emissions, classify the threat, and activate jamming systems to degrade Soviet tracking accuracy. While the SR-71 couldn't make itself invisible to Soviet radar, the aircraft's large size and high altitude made radar detection inevitable. It could reduce tracking accuracy enough to make precise missile guidance extremely difficult. Soviet fire control radars would see the SR-71 but struggle to maintain the precise track data needed to guide missiles to intercept. Soviet air defense commanders reported their frustrations through intelligence channels that American reconnaissance eventually intercepted and analyzed. One report from 1978, originating from the commander of the Moscow Air Defense District, stated bluntly, "The American reconnaissance aircraft operates with impunity over international waters adjacent to our territory, Our interceptors cannot reach its altitude at combat speed. Our missiles cannot reliably engage targets at that combination of altitude and velocity. We require new weapon systems specifically designed to counter this threat. The Soviet Union invested billions of rubles attempting to develop those new weapon systems. But every generation of Soviet interceptor and surface-to-air missile that entered service during the SR-71's operational lifetime faced the same fundamental problem. They were designed to counter the American aircraft based on observed performance. But the SR-71's actual capabilities, particularly its maximum speed and altitude, which remained classified, exceeded Soviet design parameters. Soviet engineers were always fighting yesterday's threat, trying to counter performance levels that American pilots had already surpassed. The technological disparity reflected decades of divergent development in aerospace engineering, materials science, and propulsion technology. The United States had invested heavily in titanium metallurgy during the 1950s, developing fabrication techniques that allowed construction of large airframes from exotic materials. American engine manufacturers had pursued high-temperature turbine materials and advanced cooling systems that allowed sustained operation at extreme power levels. American electronics firms had miniaturized radar, navigation, and reconnaissance systems to fit within the SR-71's limited internal volume. Every element of the aircraft benefited from American technological advantages that Soviet industry couldn't replicate. The Soviet Union could build aircraft that briefly touched Mach 3 in controlled test flights. The MiG-25, in a 1977 demonstration flight, reached Mach 3.2 for a brief period before its engines sustained severe damage from the extreme temperatures. But sustained Mach 3 crews, flying at that speed for hours while conducting reconnaissance missions, required materials, engines, and systems that Soviet aerospace engineering hadn't mastered. The gap between sprint capability and sustained cruise was the difference between an experimental achievement and an operational weapon system. By the late 1980s, as the Cold War approached its end, Soviet air defense forces had essentially conceded that they couldn't shoot down SR-71s. The aircraft continued flying reconnaissance missions along Soviet borders, and Soviet forces continued attempting intercepts, but these attempts had become ritualistic rather than serious efforts. Soviet pilots scrambled their MiG-31s knowing the intercept would fail. Soviet missile batteries locked their radars and occasionally fired knowing the missiles wouldn't reach intercept altitude in time. The American reconnaissance aircraft had established absolute dominance in the high-altitude, high-speed regime. The SR-71 program was officially retired from Air Force service in 1990, with the final operational flight on March 6th of that year. The retirement decision was driven by budget pressures and the belief that reconnaissance satellites could provide similar intelligence at lower cost. But the Air Force reactivated 3 SR-71s in 1995 after realizing that satellite reconnaissance, despite its advantages, couldn't provide the responsive, on-demand collection that the Blackbird offered. The aircraft flew operational missions until 1998, when budget constraints again forced retirement. NASA continued operating 2 SR-71s for high-speed research until 1999, making the final SR-71 flight on October 9, 1999. During its 32 years of operational service from 1966 to 1998, the SR-71 flew 3,551 reconnaissance sorties. Not one was shot down by enemy action. Not one was even seriously damaged by hostile fire. Soviet forces launched approximately 4,000 surface-to-air missiles at SR-71s over those 3 decades. Thousands of Soviet interceptor aircraft scrambled attempting to engage the American reconnaissance aircraft. The cumulative cost of these failed intercept attempts, fuel for scrambled fighters, missiles expended, radar operator time, maintenance on systems pushed to maximum performance, ran into billions of rubles, all for 0 successful engagements. The SR-71's technological influence extended far beyond its reconnaissance missions. The titanium fabrication techniques developed for the Blackbird enabled later American aerospace programs, including the F-22 Raptor and F-35 Lightning II, both of which used titanium extensively in their structures. High-temperature materials research conducted for the J58 engines contributed to development of more efficient commercial jet engines. advanced composite materials used in the SR-71's radar-absorbent coatings influenced stealth aircraft design. The lessons learned from operating in the extreme environment of Mach 3 flight informed NASA's research into hypersonic vehicles and re-entry systems. Soviet attempts to copy SR-71 capabilities led to the MiG-25 and MiG-31 interceptor programs, neither of which achieved the Blackbird's sustained high-speed, high-altitude performance. Soviet reconnaissance aircraft development remained focused on subsonic or low supersonic platforms that couldn't match the SR-71's invulnerability. The Soviet Union never developed an operational reconnaissance aircraft capable of sustained Mach 3 cruise at 85,000 plus feet. The technological gap established by Kelly Johnson's team in the early 1960s persisted through the entire Cold War and beyond. Multiple SR-71s are preserved in museums across the United States. The most prominent is displayed at the Smithsonian National Air and Space Museum's Stephen F. Udvar-Hazy Center near Washington, D.C., where visitors can see the aircraft that set the transcontinental speed record on its final flight. Other Blackbirds are displayed at the Museum of Flight in Seattle, the Strategic Air Command Museum in Nebraska, the Pima Air and Space Museum in Arizona, and multiple other locations. These museum aircraft serve as monuments to American aerospace engineering achievement and reminders of an era when manned reconnaissance aircraft routinely penetrated hostile airspace with impunity. The SR-71 remains the fastest air-breathing manned aircraft ever operated. Modern reconnaissance relies primarily on satellites and unmanned aerial vehicles, neither of which can match the Blackbird's combination of speed, altitude, and responsiveness. Reconnaissance satellites orbit on predictable paths, allowing adversaries to hide activities when satellites are overhead. Unmanned aircraft offer endurance but lack speed, making them vulnerable to advanced air defenses. The SR-71's unique combination of capabilities, rapid response, extreme speed, high altitude, and essential invulnerability, has never been duplicated or replaced. In the cockpit of an SR-71 cruising at Mach 3.2 and 85,000 feet, pilots experienced an environment unique in aviation history. The view from that altitude showed the Earth's curvature clearly. The sky above was black, the edge of space visible during daylight. The air pressure at 85,000 feet is approximately 1% of sea level, meaning pilots wore full pressure suits identical to those worn by astronauts. Any cockpit depressurization at cruise altitude would kill unprotected crew members within seconds. The cockpit temperature, despite the 900-degree skin temperature mere feet away, was maintained at comfortable levels by sophisticated cooling systems that circulated chilled air through the pressure suits and cabin. The experience of flying faster than a rifle bullet, higher than most surface-to-air missiles could reach, knowing that hostile air defense forces were attempting and failing to shoot you down, created a unique psychology among SR-71 crews. These pilots and reconnaissance systems officers were conducting missions deep into hostile airspace, or along its borders, relying entirely on their aircraft's performance to keep them safe. One engine failure, one hydraulic malfunction, one fire or systems failure at Mach 3.2 and 85,000 feet could be catastrophic. Yet the SR-71's safety record was remarkable. Only one aircraft was lost due to mechanical failure during operational service, and both crew members ejected successfully and survived. The contrast between American and Soviet capabilities couldn't have been starker. American pilots flew missions knowing their aircraft could outrun and outclimb any threat the Soviets could deploy. Soviet pilots scrambled their interceptors knowing they couldn't catch the reconnaissance aircraft they were supposed to engage. Soviet missile battery commanders fired their weapons, knowing the engagement geometry made intercept nearly impossible. Soviet air defense commanders wrote reports documenting their inability to stop American reconnaissance flights. The psychological impact of this asymmetric capability was profound. For Soviet military leadership, the SR-71's invulnerability represented a fundamental failure of their air defense doctrine. They had built the most extensive, sophisticated and expensive air defense network in the world. Thousands of surface-to-air missile batteries, hundreds of interceptor bases, overlapping radar coverage across the entire Soviet Union and Warsaw Pact territories, tens of thousands of trained personnel, billions of rubles invested in equipment and infrastructure. And despite all this investment and capability, one American reconnaissance aircraft design could violate their airspace borders at will, photograph their most sensitive military installations, and return to base untouched. The final admission came in 1992, after the Cold War had ended and the Soviet Union had collapsed. General Pyotr Denikin, who served as Commander-in-Chief of the Soviet Air Force from 1991 to 1998, gave an interview to a Russian aviation magazine. When asked about the SR-71, he stated simply, "The Blackbird was untouchable. We tried everything we could think of. We never came close to shooting one down. It was the most frustrating operational challenge of my entire career." That assessment, from the officer who commanded Soviet air defense forces during the final years of the Cold War, encapsulated 3 decades of failed attempts to counter American aerospace superiority. Soviet air defense doctrine had been designed to dominate the high-altitude warfare environment of the 1960s. The SR-71 flew reconnaissance missions using technology from 1985, starting in 1966. For 32 years, 4,000 Soviet missiles tried to stop it. For 32 years, thousands of Soviet interceptor aircraft scrambled attempting to engage it. For 32 years, the SR-71 flew home. Every single time.